Hello, everybody. Thank you for joining today's webinar entitled Defining the Transport Environment. Before we start, however, I wanted to go over a few quick things. So this is a Lansmont Corporation webinar, and Lansmont falls under the umbrella of the Physical Properties Testers Group, or PPT for short. The PPT is a family of brands, all of whom are experts in the design and production of physical properties testing solutions. These solutions cover a range of physical properties, including tensile and compressive strength, torque testing, textile analysis, and real-world dynamics, such as shock and vibration. The other companies in the PPT family are McMesson, James Hill, and Aluris. If you're interested in learning more about any of our partner brands, you can visit the PPT page and see the content and on-demand webinars we have available. I've already put a link in the chat box at the start of this webinar, so you're welcome to visit that. And if you want to contact me for that particular URL later on, you're more than welcome to do that. I want to introduce some people on today's call. So Eric Jonason is our presenter for today, and my name is Sharon Smorenberg. I'm one of the organizers. Then we have various support staff throughout the United States, Europe, and Asia. As always, please feel free to ask questions. You can use the question box throughout the webinar to type in any questions that you may have. We will then address these questions at the end of the webinar. The webinar again will be recorded, and you will get a copy of the recording to the email that you registered with. If you want to review anything for additional clarity, or if you have a colleague who is interested in attending but wasn't able to make it, please feel free to pass the recording on to them. We usually try and make the recording available the next day. If that's not possible, the day after that. So it should be within your inbox quite soon. And with that, I will turn it over to Eric for the start of the webinar.
Okay, thank you very much, Sharon. I appreciate it. And thank you for those that are signed in online. I appreciate the interest and hope to provide you with some interesting information associated with the topic I'm going to discuss here, which is really the step one of Lansmont's 6-step method, which is associated with defining the transport environment, basically meaning defining or characterizing all the hazards that are present in the transport environment or supply chain. A little bit about myself, or if anybody is unaware of who I am. My title is Vice President of Technology for Lansmont Corporation. I have been with Lansmont Corporation my entire career, which started over 34 years ago. And I have spent much of my time in various roles within the company, from starting in customer service, teaching people how to use our equipment, and then eventually working for 11 years in our own test laboratory. So I have a lot of experience with actual hands-on testing, operating and managing a test laboratory. And for many, many years, I've been directly involved in measurement activities, meaning exactly what I'm going to be talking about today, using data recorders to go out in the supply chain and try to measure, summarize, characterize, and understand what it takes place in that supply chain. So I'm speaking in, basically from an application side as I talk today, and giving you some input and guidance as to how you would go about this process. That being said, I'm going to plan to turn my camera off so I can just focus on the content here and not eat up bandwidth, because I do have some videos involved. So with that, I'll come back on at the end of the presentation, answer any questions, turn my camera back on. Thank you. So I'd like to start, once again, I've used this transport packaging design fundamental in many of my presentations, but I think it's good for setting perspective as I present, the remaining content. And it's just this idea that the product durability plus the protective characteristics associated with packaging have to work together to overcome or address all the hazards that are present in the supply chain or the distribution environment. And of course, from the Landsmont perspective, since we are primarily a shock and vibration company, that means those types of dynamic hazards, right? All the bad things that can happen from a shock and vibration, maybe even dynamic compression. So as we show this basic fundamental, it obviously there's a lot of complexity built into that. Yet what's important to take away is that it's of the strong opinion that it's important to know a little bit or a lot about each one of these three categories. You need to know something about your products, you need to know something about your packaging materials and their performance. And what I'm going to talk about today is you need to understand those hazards in the environment, because why do you need to know that? They really set the performance kind of criteria or requirements for product design and package design. And that all comes from, what does that environment look like? Another way of looking at that real quick is we talk about the hazard intensity, when in the supply chain, all those distribution hazards that can occur there. And this is just another way of saying the product durability plus the protective packaging has to equal or be greater than kind of the severity associated with those hazards. But what does that mean? What do we really get from trying to understand all those hazards? Well, we use that, right? I mean, for the most part, we use that information that's associated with the measured intensities or the knowns from the environment to drive the type of testing that we perform in the laboratory, right? So we basically take that information from supply chain, convert it to being actionable, from data to being actionable by turning it into testing inputs and methodologies. Because of this, do that, basically. And so that's kind of a good way of understanding why we, one of the key reasons why we go out and we do these measurement efforts. And that can either be, again, company specific measurement efforts or industry standard measurement efforts. So supply chain. Landsmont practices what we call this field to lab methodology, right? And what basically that means, measure what all those hazards that occur in the supply chain that pose, again, risk to our packaged products, and then use those measurements to drive testing, laboratory testing. Pretty simple, but it's really kind of our, ethos. That's what we practice, and we really are always thinking in terms of not just going out and measuring things, but the intent. It's more important to understand the intention of the measurement. What are we trying to learn? What are we trying to achieve from this? How will we use the information that we capture? And these kind of looks, hopefully the video shows, but these are just, the ideas of going out and measuring very specific types of dynamics and how we might be able to then use those measurements to drive the specific type of testing, whether it's drop testing, impact testing, vibration testing, even dynamic compression testing. And the tools that we use from the Landsmont side of things are our SAVER shock and vibration data recorders, right? So, and again, I'm presenting this from the Landsmont perspective. There are other people that make these types of devices. Landsmont, that's one of our key tools, in that whole field to lab process is the measurement devices themselves. That drives so much of what we do in terms of our overall product development, from the physical testing equipment side of things. We use kind of our understanding of all these types of dynamics really to drive the type of equipment that we might develop and the performance of that equipment. And so this is the key. These types of devices are the key, and this picture shows a number of different instruments. There are reasons why there are different instruments, different performance kind of capabilities associated with those instruments, but basically that's what we use. And what I like to say is, before anybody begins doing these types of characterizations of the supply chain or distribution environment, stop. Before you start, pause for a second and answer some questions, or try to address some questions, key questions, because it isn't necessarily an easy process to go out and measure and understand, to the point where you are generating actionable results. Okay, so data by itself is meaningless, right? Without some kind of context associated with it. It's easy to generate data. It's more challenging to generate information that can be acted upon, that's actionable. And so, a lot of times for us, there's a series of questions that we either ask ourselves or ask our customers if we're assisting people. Why are you doing this? And that might sound like a pretty obnoxious kind of question, maybe, or snide, but quite frankly, it's important to understand why are you doing this measurement? What do you really hope to learn from this measurement? And what do you know about your product or products, your packaging, and your transport environment, just to begin with. So it's important to document some of these things up front, because that really drives then the approach as to how you go about doing a measurement. Not just even about how you say schedule the project itself, but literally how you for instance, program one of these instruments and install one of those instruments. It's all driven by, what are you trying to accomplish? What are you trying to learn from the effort? Another interesting, some questions when people say, why are you doing this? Why are you measuring? And some people say, even recently in some of the events that I've attended, don't we know all these answers already? Isn't a truck a truck? Isn't a train a train? Isn't, what we knew about a truck 10 years ago, 20 years ago, or 30 years ago, a truck trailer, or a box car on a train, or an intermodal container? If you defined it 20 years ago, do we really need to keep doing this? And the answer or answers are, yeah, we do know quite a bit, and some things do remain fairly consistent. But there are reasons, obviously, for new and different measurement projects. The list can go on and on as to why you might do those, but just an example of why that's current kind of trend when you talk about sustainability in packaging, right? And the packaging side of things, or products for that matter. The whole idea, there's a number of ideas associated, or goals associated with sustainability, but one of the key ones, in our world, is that it means use less packaging materials, right? I mean, obviously use more environmentally friendly materials, but key to in many cases, it's do it with less. And so we say in this, this is a snapshot of an ad that we had run once upon a time. It says less is more, but how much less? And the idea there means, okay, nice goal and initiative to use less materials, but what happens when you reduce that to a type of material or amount of material that causes not only package damage, but maybe product damage, damage to the product inside? That is that's an issue, right? And so this one slide just is an example of what those implications are. If you look across the bottom of this slide, it shows basically packaged water bottles that were once upon a time in a complete corrugated fiber container. And with time, you see that's changed to using shrink wrap in a tray, and then shrink in a pad. There's no tray on the third image. And then there's just shrink only, unsupported shrink on the far right. And so these well-intended sustainability initiatives have led to, in this type of an example, a reduction in structural primary, secondary, and sometimes tertiary packaging, which results in more dependency on things like stretch films for load containment and stability. And that can amplify issues associated with load integrity, load stability, and obviously damage. So this is a very real situation where you say, oh, well-intentioned, but kind of troubling results. And what's the cause of those results? Well, is it really any different? It's the same truck, maybe, or the same type of transport. So what really changed here is not the transport, but the packaging. And if you think of that transport packaging fundamental that I show at the very beginning, which is product plus package has to be equal to or greater than the environment. Well, the environment probably here didn't change any. It's the packaging, or it's the combination of the product and the packaging that changed. However, what's causing this type of damage is the dynamic. A dynamic in a way that we haven't, let's just say over a long period of time, at least in my career, we haven't really focused on. We focus on shock and vibration, meaning when we say shock, big bumps from either going over uneven surfaces or rough surfaces on the road. It could be backing into a truck dock. It could be handling from forklifts. It could be any number of things. But this type of dynamic really that would cause this is something that's like from a truck accelerating or braking, or in this case, turning. You notice in this case, the loads are shifted to the side, right? It's a lateral shift, not a longitudinal lengthwise shift. It's from the side, and it's probably associated with turning. And that's we don't think of that in terms of shock or vibration. We think of it as a unique characteristic that we really, over time, haven't focused on as much as we have, let's say, in the last 5 to 10 years, as a testing community. Why? Because it's by definition, from an acceleration perspective, or G's, it's a low amplitude type of dynamic, but it has obviously big consequences. So things like this, these are reasons for us to keep digging into the root cause analysis of why there are problems in the field. And so this is just a video kind of showing, that's looking in the back of a truck at a couple pallets, hard to see behind some plastic separators, but as the truck puts on the brakes, you notice the pallets, the loads shift forward. And that's the kind of information that we're trying to capture and understand to drive new types of testing, different types of testing, potentially, in the laboratory that will simulate those unique dynamics. So this is just another example of why we continue to do these types of measurements. It's usually driven by what's perceived to be some unique characteristic in the supply chain that's popped up, as kind of an issue moving forward. And just as another example, all right, that's an AGV, automatic guided vehicle. And so imagine, what do we know about that, right? What do we know as a community about what that environment looks like from handling? You could think that you could program it to be safe and secure from its handling perspective, which in theory you can program it that way. The reality means let's verify, but through measurement, how well it handles it. But what I'm even aware of from my side of things is some people in, say, not only where AGVs are being used, but in automated storage facility where robots basically move unit loads and then they go up into racks, storage racks through elevators. All of that is completely automated. And some people are looking at opportunities from a sustainability perspective to not use stretch films, for instance, on their loads when they're in those facilities, because it's because in their overall supply chain, the way the operation works is those loads come into the facility, they go into storage, and then they get picked apart, and then they come back out maybe as a half pallet instead of a full pallet. So instead of wrapping them on the inbound, unwrapping them, and then wrapping them again on the outbound, some people are saying, well, how about I just don't wrap them? How about I just store them unwrapped and bring them down unwrapped, and then wrap them before they go out for their final transport to the end destination. So that sounds like, again, a relatively benign or simple thing, but huge implications if you don't wrap those loads, and these AGVs might handle them in a way that you didn't anticipate. even as gentle as it may be, now that you're not wrapping anymore, how stable are those loads? So it's another reason to go and characterize, right? And go and measure and define that environment, because it's unique. It's new idea and it's unique. And then, these are just other examples, right? So what about the medical side of things? That was blood, packaged blood. But what about biological products, vaccines, or certain types of drugs that get transported uniquely, right? In this case, drones, which is more and more becoming more and more of a reality, especially in certain areas of the world, like where there's not huge population density, say Australia, or areas in Africa where it's probably more, it is more prevalent to use these types of supply chains or modes. And what do we know about that? Again, and again, there might be some assumptions even from my side that says, it looks exciting, but it probably isn't that. Comparably, it's probably not that severe of a vibration environment, for instance, as compared to a truck. And that may be the case, but in the medical world, you got to prove it. You can't just assume it and say, yeah, I bet it's not as bad, or I know, I'm confident. Well, that's not good enough in that world. You actually have to document things that you do know. So it's just another area to go, kind of warrant going out and continued measurement and characterization of a supply chain. So kind of key ideas of why we do this. We need to know what happens, right? We need to know, what happens from a shock and vibration perspective, how much of it happens, how frequently, for instance, how often does it occur during transport and supply chain, and when it does occur, how severely is it happening? I get bumped, 10 times during transport. How big are those bumps? What do I understand about the true kind of fidelity of what that bump looks like? How much energy is associated with that? Those are all key reasons to go and try to understand it. From a general instrument installation side of things, that's also, how do you install one of these types of devices? Well, it depends. Too many of those type of answers where it depends, but it does. It depends. Are you trying to understand how packaged products respond to dynamic or transport dynamics, or are you trying to understand the inputs? And in most cases, you probably want to know a little bit about both. So this is an example, as simple as it is, of an instrument that's packaged in a transport container, a small one. But you can think of it as a parcel. I'm simulating a parcel situation. It's got foam around it. This is actually a video produced by Virginia Tech, who does this type of, all the various packaging universities do this type of research at some level. But they were doing a audit of the last mile, kind of think of the last mile delivery process when you order something through Amazon or Walmart, Sam's Club, maybe even the USPS, how things are delivered in that last mile. So what we do is we package these instruments and we do things like calibrate that in the laboratory. So what that means is that we put the instrument in there, we shake it, we drop it in a controlled environment so that we know if I drop this device in this orientation from this drop height, this is what the response looks like. And once we understand that relationship, we can then send those types of devices out in the supply chain and obviously measure responses. And from those responses, we can, in a number of different ways, you can't necessarily equate it to exactly what happened, but you can basically make a determination on, well, what would have caused that? What is the equivalent input that caused that? How high was it dropped? How hard did somebody have to hit that one way or the other in the supply chain to generate that response? So that's a very common, kind of approach. That's a small obviously a very small parcel package, but there's a number of different ways to develop what we would call instrumented decoys like that. And it can be, different varying sizes of packages, decoy packages, or even things like crates, quite frankly, where you can instrument like that and you're measuring responses. And the way that you get again, kind of generate confidence on how to evaluate field responses or supply chain responses is to put it through known input conditions in the laboratory before you ever go out and capture those field results, because it gives you the right perspective. And then of course, the other type of instrument installation is where you're literally attaching devices to the transport vehicle, be it a truck, a train, maybe the cargo floor of an aircraft, if it's placed on an aircraft. This is an example of a instrument, more of a kind of comprehensive instrumentation setup, where we have a couple instruments mounted to the floor of an intermodal container. Those instruments are connected to additional instruments on the bottom pallet, which is connected to additional instrumentation on the top pallet. And in this type of an example, what we're trying to understand is not only what the input dynamics are, shock and vibration input dynamics from the vehicle, but also what the responses are from the loads, to say, all right, if I put in, or if the floor vehicle shakes like this in this orientation, up and down or side to side, how is my package product, responding to those types of inputs? And so that's an example, again, a very, common example of where instrumentation is used right on the transport vehicles themselves. And why do we do it that way? Well, many cases when we're doing these characterizations is because in the laboratory, that's what we're trying to simulate, right? That's what our vibration tables are trying to simulate. That might be what let's say an incline impact test, a incline impact test sled, when you're bumping it up against the wall, that might be the equivalent of trying to simulate a truck backing into a dock. And so you're looking to understand what that real world environment looks like from a impact severity, so that you can use that to simulate that same type of dynamic or input in the lab. And this is what, kind of what one of those fully instrumented setups looks like before you shut the doors and head off. And then what we do oftentimes is use cameras. It's not just necessarily when we go out and characterize, are we using instrumentation, but we're also using cameras, because that you can think of, video or photography as just another form of data, right? That helps document and characterize what takes place in supply chain. So this type of video or data tied to our dynamic data allows us to see what visually see what the responses are to our packaged products, as it relates to whatever the measured input was on the floor. So very powerful pieces of information, again, that helps to characterize and define environments. The instruments themselves, this is a snapshot from our software. Our software that we use is called severity to drive our program and analyze the data that's captured and produced from our savers. And this is kind of the, there's a lot of information here, but what's important to understand is that the way instruments work is they are event recorders, right? You turn them on when you send them out in supply chain, and they are capturing or storing data based on certain conditions. They don't just run or capture one continuous stream of data throughout the whole journey. You could do that in some cases for some amount of time, but most people don't, because it generates a huge amount of data that you then have to deal with eventually. So what we do is we trigger these instruments. It's not just us, that's just the common approach, whether it's our instruments or even other instrument providers. They work on a triggering condition. And so what I'm showing here and highlighted in red, one of the modes these instruments operate is based on a signal trigger or a threshold trigger that basically says, if I experience or see a bump of certain magnitude, and we define that in terms of G's. If I see a 5, in this example, I'm using this is showing a 5G trigger. It can be a half G trigger, it could be a 20G trigger. But once I see that magnitude, I say, ooh, that's a big thing, store that event, for a certain amount of time that's based on the programming conditions that within that red box, store that in the memory, and then wait, stop recording, wait until it happens again, if it happens again. So that's a signal triggered condition. And you can think of that as, is a way of capturing big, high energy, kind of, more of the nasty shock events, right? That would occur. Only record those things if and when they happen, but not continuously. The other side of how these devices work is on a timer triggering interval, basically an interval triggering. So you wake the instrument up. They really never sleep. So it's we call it wake up interval, but they really don't sleep. What they do is they store information based on a timer interval. So every 2 seconds, every 2 minutes, every 5 minutes, every 10 minutes, take a recording of time, store it in memory, go to sleep until the next interval. And what that does is it generates, basically allows you to tell a story of what's taking place during a transport from point A to point B. So this now is a screen from our analysis side of the software. Once we're into the analysis, what I'm showing here from the left to the right is time. So the start of a measurement journey to the end. So it might be hard to see in the small numbers, but it basically starts at 8 o'clock in the morning and ends at 5 o'clock, 5:30 in the afternoon. And it's not showing any data right now. But so the top section of this graph would show vibration data, and I'll show you that here shortly. And the bottom one is for the climatic conditions, temperature, relative humidity, and altitude. And so what we do is the instrument triggers, right? It collects events periodically based on those triggering conditions throughout that whole journey. And basically, from all that data, you're able to tell the story of what occurred during that journey. So the height of those red bars on the top graph basically speak to, in this case, the severity of the dynamic vibration measurement at that time. So the higher those bars, the more severe the vibration, the lower the bars, the less severe. And where there's basically no information or flat, that's when the vehicles, for instance, are stopped, not moving, parked for some reason. And so what this data is from a LTL measurement that was performed once upon a time, which means less than truckload. So those types of trucks delivery is something that where it stops and goes many times during a day. Usually that type of transport is around a metropolitan area, and they make multiple deliveries during a day. And so we were trying to measure and understand what that looked like. And so that's why you see periods of activity and periods of inactivity. And along with that, we get temperature, humidity, and in some cases, atmospheric pressure, which is altitude. And for each one of those red bars, so I'm pointing to the biggest one in this example, which is the most intense or severe vibration event that was measured. For each one of those, we capture what's called time history data. So that is 2 seconds. So for every one of those red bars, there is 2 seconds of raw data, acceleration data, that is recorded and in memory. And it's not only for vertical vibration, but it's for vertical, lateral, and longitudinal data, because the type of accelerometers or sensors that are in those sabers is recording X, Y, and Z, or all those 3 directions, triaxial accelerometer. And so we have that time history. And from that time history data, we can then convert that automatically into vibration data, or what's called frequency domain data, PSD, power spectral density. And that is what a PSD is, what can be programmed commonly programmed into a vibration test system in a laboratory if it's got random vibration testing capability, a hydraulic random vibration test system. And so for every one of those events, which could be thousands of them that are recorded during a recording session, there is a power spectral density plot associated with each one of those events. And at the end of it all, we have the ability to create what we call summary power spectral densities that are like a composite based upon multiple events, right? And that might be a composite that's based upon 10,000 events, all averaged together, or some type of statistical subset of that total population. We can look at the things like the upper envelope, the average, the 99th percentile, the 95th percentile, the 90th percentile. There's different ways of looking at the exposure, the vibration exposure to that entire journey or that population. From a shock perspective, that's the other thing that we capture with these, right? Shock and vibration, they're different. Shock pulses are described by their waveform. Looks like a waveform. This is an example of a shock pulse. We describe that in terms of its amplitude in G's of acceleration. That's how severe from a amplitude perspective it is. We also define shock pulses in terms of their duration, how long they experience that type of shock amplitude. And we talk about their frequency, which is associated with the duration. We can calculate the frequency in hertz associated with a shock pulse. Another key part of looking at shock data is that when we integrate a shock pulse, we calculate what's called delta V, or velocity change. And so that's calculated by really the area underneath of a shock pulse, right? So it's, again, something that's automatically done through software, one way or the other, data acquisition software, but it's basically equal to that area that's showed there, that's shaded, the area underneath a shock pulse waveform. And what's important to understand about that is that velocity change. So when we calculate that 200 inches per second that's shown on the screen there, that represents that area. And that speaks to my second bullet point there. It says velocity change is proportional to energy. Velocity change doesn't equal energy, but it is directly proportional to it. So a lot of times I think about it or try to describe it as the oomph, so to speak, of a shock pulse. 30 G's just by itself, the G level or the duration by themselves don't necessarily speak to the absolute severity of a shock pulse. The delta V does, because it's really more of a descriptor of the total energy associated with that shock pulse. Additionally, you can calculate, there's a way of calculating based upon that number what the equivalent free fall drop height would be required to generate that type of velocity change. So that number is really important when we do these studies or measurements to speaking to the severity of any given event. It's much more, much more than just taking a G value. G values by themselves are important, but not by themselves, or they're not enough by themselves. A shock pulse really has this full definition of G's, duration, and delta V that speaks to it. And then one of the ways we can summarize that information, in our software, or anybody could, is basically by a plot like this, which is an acceleration on the y-axis versus delta V on the x-axis. And it's a way of looking at all the events in a population such that what it says is, if it's got high acceleration value and it's got high delta V value, that's bad, comparably bad, severe, or much more, of much more concern, those types of events, than things that are down in the, on the lower left, either lower or left-hand side of a plot like this. It's a way of quickly kind of looking at a population of events and saying, there's my big concerns, because they have not only high acceleration levels, but delta V associated with them. So kind of getting closer to the end here, what I wanted to point out is, in my experience in doing all these studies, back in, let's say, even in the mid 2000s, what we realized, a number of people, is that you would see presentations at various, events, conferences around the world, and you would question whether the data was collected correctly. And what does that mean? Quite frankly, that's could be based on individual opinions, right? Whether it was done right or done wrong, or correctly or incorrectly. And quite frankly, some people might have questioned the way that I would have collected data at that time. So we realized that there's probably an opportunity from the kind of a consensus body or a standards organization to say, hey, wait a minute, let's see if we can kind of agree on a way for everybody to go about doing these collection efforts so that we have some kind of additional confidence in the resulting data. And so I'm going to just mentioning here that in 2008, ISTA, the International Safe Transit Association, established what they called field data workshops, the first time they ever did it, and it was done in 2008. And I actually attended this at the time, and there was a couple of them. There was one that was done in North America for a couple of years, and one that was done in Europe, with the very idea of how, you can see on this slide from that time, how to create meaningful and efficient laboratory vibration tests from field data, how to do it. And so that's really, not only just about collecting data, but how to then use the data to drive testing. So these field data workshops started with ISTA back in the 2008 timeframe. So that's 15 years ago. And what resulted from that, not just these conferences about how to go about it, but was really then documentation on the ISTA side of things. So ISTA has available, not to members and non-members, quite frankly, what they call data collection standards. So I share this because I think these are very valuable tools and pieces, assets that exist right now to help people understand how to do this, but also to do it the same way as other people might be doing it. And so these ISTA data collection standards basically address how to record from transport atmospheric data, shocks, impacts, drops, and vehicle vibration. And I'm just showing, these are big documents. I can't share, obviously, the whole documents, but it just is trying to give an idea of these, get right into the details of how you set up a data recorder. And the nice thing about this is that, it's kind of a common, allows for people who might be intimidated about how to go about one of these studies or any of these studies, how to set things up, how to control, that setup and save that as a standard setup, and not only for shock and for vibration, or not only shock, but also for vibration. And it makes things, it gives the collection, the data that's collected, a level of confidence, quite frankly, that it was been done with some minimum level of standard, clarity from the collection side of things. It doesn't speak to the analysis, but it says, if we're going to collect it, we're going to collect it the right way. And we have agreement from a number of experts that got together once upon a time through ISTA to set these standards. And then what followed from that is the ISTA data analysis guidelines that says, okay, now that you went out and collected shock and vibration data, here are some guidelines for how to go about analyzing it with the interest or the intent to use that data in a laboratory setting, right, to drive laboratory testing. And so the idea for really also from ISTA, obviously ISTA is one of the organizations that sets test standards, right, that simulates distribution dynamics. And there's obviously a number of their standards, but realize that any standards, whether it's ISTA, ASTM, those are based on data, right, one way or the other. They're based on data. Some of those standards can go back 20, 30, 40 years ago, but they are based upon something, right, that were probably data that was collected with maybe technology in that time frame. It also could have been based on observations. but they are based on data. And so, ISTA also realized that they had an interest in establishing these standards so that anyone that would provide data to ISTA with the intent of creating, let's say, a new standard or asking for a standard to be updated, well, you would have some level of confidence as, again, the ISTA, let's say, technical committee or the standards committee to say, oh, okay, you're going to provide me data. Well, was that data collected per our data analysis or data collection standards? And if so, again, it's like, all right, we'll take a look at it, and we very well may use it. So it was really well intended reason for setting those standards and establishing these guidelines. And what I want to point out is that even now, if you go to ISTA's website, they, under education, they have one of their offerings is something that's called distribution data collection analysis courses, and there are 4 modules there that can be done online study. And just so happens, even yesterday, they on LinkedIn there was a posting highlighting this, and and I know the people that were involved in creating this and that deliver it, and I just know that it's a really valuable tool and asset from the ISTA side of things that's available to anyone, quite frankly, again, member or non-member, for a fee to go participate in and take those courses. Very helpful in understanding the whole idea of environmental data collection, how to do analysis of shock data, how to do analysis of vibration data. So I want to point that out. Obviously, Lance, myself, there are people that can teach people how to do this if they need help and assistance, but this is a really nice resource from an industry standards perspective that is available and out there. Okay, so that's all I was going to talk about today on defining the environment. I did want to just mention real quickly that Thursday, September 21st, I'm going to deliver the next webinar that's based on the 6-step method. That's going to now get into the product side of things, defining shock product fragility. So kind of changing it, and it will be technical and talking about shock testing and giving examples. So I wanted to point that out. Hope that some people are able and interested in attending that. And with that, I'll give it back to Sharon and myself if there's any questions. Thank you for listening and participating.
Thanks a lot, Eric. So if there's any particular questions, then please go ahead if you haven't already and pop the question into the question box, and we will go about addressing them now. So Eric, a few questions have already come in, so I'm just going to read the first one. Can the saver sensor also be used to measure the vibration of the drum of a washing machine?
Sure, it could. Yep. Yes, no problem. I mean, again, it as long as there's the savers themselves, obviously have a footprint, a size. So you have to, is it capable of being attached to whatever you want them to measure, like the drum? But some of the savers, there's one called the Saver 9X that also allows for additional external accelerometers to be attached to it. So they can be very small devices that attach to the saver with a cable. And those small, accelerometers can be placed obviously on smaller items or areas that can't necessarily hold a complete saver. But yes, they can for sure. No problem. They could do that. And I would be happy to talk about that with whoever at some point further if they're interested.
Okay, the next question. What is the capacity of data saved by the saver?
Yeah, the memory on a saver, believe it or not, is actually very small in terms of what everybody's probably familiar with in terms of gigabytes or megabytes. It's actually only 128 megabytes. Sounds probably ridiculously small, and it is small by comparison of our mobile devices and things like that. But realize that when even if you fill up a complete saver with memory, you can collect as much as like 40,000 individual time history events, right? And each one of those time history events can be like upwards of 2 seconds of data on 3 channels. What it means is that's a lot of data. And when you collect all that data, it takes resources and horsepower of a computer to process all that data and analyze and summarize all that data. So it's, even at the 128 megabytes, it's a lot of data. We're moving in a slightly in a direction of increasing that slightly, even on the current models. But it's like a blessing. I don't want to say it's a blessing. It's going to be added capability, but it comes at a cost of it's just more data. And maybe people want more data, but the current capability is pretty large. When you're talking tens of thousands of events, you can do a lot of information. And you think in terms of, I'll just even say shock events. Shock is a hazard, right? People are concerned about shock in things in transport and supply chain. You better not have any more than a handful or less than a handful of big shock events that occur during transport, or you got problems. You got really big problems. So do you need to have 5 gigabytes of data, shock data? Most of that will be insignificant data, quite frankly. And even from a vibration perspective, if I record every 2 seconds for 30 days, I can draw or create a really nice kind of characterization of that environment versus leaving the recorder on continuously and then having to stream together gigabytes of data. So it's a cost benefit thing. So right now, again, 128 megs, that's what it's got, but the equivalent of that converts into tens of thousands of dynamic events that can be captured in that memory.
Thank you. Is there a guideline for how many trips of the same real-world route to record to ensure good lab simulation?
That's recommended, and more is always better. So one is not enough, and 30 is wonderful. The reality is these studies, again, they can be quite resource intensive to undertake. The data, quite frankly, the data reduction and analysis is the easy part. Typically, it's the logistics, the project management that takes a lot of time and coordination to handle these, to do X number of replicate shipments. So, yeah, again, more is better than less. We usually, I personally like to try to shoot for like no less than 10 replicate shipments. And that does, when I say replicates, that means different day, different truck, different vehicle, to try to add or account for some variability in the supply chain, if there is going to be any. So, I shoot for no more than 10 no less than 10. And a lot of times what I also do when I do these types of studies is I look, it's even from the vibration perspective, when you look at each one of those, let's say measurements, you record tens of thousands of events, I get a summary from each one of those measurements, trips. And I can look across those trips. So trip 1 looks like this, trip 2 looks like that. And if they're extremely different, it says, yeah, I better keep going because there's a lot of variability in the data. But if trip 1 looks, quite a bit like trip 2 and trip 2 looks a little bit like trip 3, that gives you confidence that you've addressed the variability side of things and says, all right, I'm good with 10. I don't feel like I need to do more than that. You basically, let the data steer whether you feel like you need to do more or not. More is always better, but there are, again, challenges associated with that, typically for people.
Okay, next one. What is the lower frequency limit for the built-in accelerometers?
0.5 hertz. 0.4 hertz, and with some of the instruments. we have one instrument called the 3D15 that uses a DC response accelerometer that is used for making, measurements down to DC. So we do have one instrument that can handle very low frequency. The rest of the instruments are down to 0.5 hertz, which in the transport environment is very low, I would say, my opinion. You don't see that type of dynamic on, like, truly dynamic in, let's say, vehicle vibration or any type of transport vibration. Even in shock, it's usually a higher frequency. But for the DC response type measurements where trucks are turning, braking, those are low frequency type of dynamics. And so that's the right type of instrument to use for those measurements.
Okay. If the saver is not mounted base down, can you change the XYZ orientation to make processing easier to understand?
You can obviously, I'm not exactly sure what that question means, and certainly feel free to reach out to me directly, whoever that is. But you can obviously mount the saver in any different orientation. In XYZ. So that, if you mount it on its side, I don't know if you can see my instrument here. So yeah, normal mounting would be in this orientation. This is, considered the bottom. Obviously the top has got the overlay on it. So a normal mounting would be to mount like that on say on a truck bed or a container. But maybe you have to mount like this, and that's okay. So in that case, this in our terminology is channel 1 or the X direction. But you can change in the software, you can change the labels on the data so that you can say, channel 1 is now vertical instead of channel 1 is lateral. You can specifically, type that in or whatever, name that channel, rename that channel, so that when you look at the channel 1 data, you go, oh, wait a minute. A lot of times you might question, was channel 1 vertical or lateral, or which direction was it? But you can literally, right in the software, change the naming of that channel so that, down the road, you go, channel 1 was vertical. I don't know if that makes sense or not. And I don't know if that addresses the question, but if it didn't, feel free to reach out to me directly.
Thanks, Eric. And then I think it's what looks to be the last question. We use the 95th percentile of shock data we recorded, but get accused of over-testing. Is 95th percentile the industry standard?
I don't know that there is an industry standard on shock or vibration data, quite frankly. That's a really good question. Even on the vibration side of it, it's what do we test to, and I think it depends on obviously company by company, maybe product by product. What's your tolerance for some level of damage? If you're a high volume, low value or low cost products versus low volume, high value product. So, the extremes might be, not to devalue cereal, but if you are shipping cereal, cornflakes, you ship a lot of them, or paper towels. It was one of the examples I showed earlier. You ship a lot of paper. The cost of that paper is not so significant. Maybe that you have a greater tolerance for some amount of damage than if you're shipping mobile phones or semiconductor inspection equipment. That's $500,000 per product in a crate. So you might, or if you're a vaccine that's going to be injected into somebody's body, you're going to test at the 99th percentile, if you can define that, versus the 90th percentile, right? So it kind of depends on who you are and how much risk you're willing to take. And so I can't, even with shock, I'm not sure who's asking the question, but I don't know if I have enough experience, with anybody to say most people test at the 95th, 99th. My experience on more of the vibration side is if you test at the 99th percentile, you better be careful about how long you expose your items to that percentile, because it's pretty nasty. And I would expect the same shock if you jump up to the 99th percentile. you better have some durable products and packaging.
Awesome. Thank you so much, Eric.
Yep.
I don't see any more questions, but if there are any follow-up questions you'd like to get answered, please send them to Eric at the email shown on the screen. And I've also put his email address in the chat box for easy reference. So again, thank you so much for joining us today. And we really hope that we'll see you for the next installment in the webinar series, which is defining product shock fragility. And that will take place, like Eric said, on September 21st. But for now, thank you very much. Enjoy the rest of your day, and we will be ending the webinar.
Thank you, everybody, and thank you, Sharon.